All right, we're going to be solving some differential equations today, but we're going to be solving a very, very specific kind. Now, last day, we did the population growth problems, and we were able to do those because of the nature of the problem. We did the Newton's law of cooling. The nature of the problem made it fairly simple. So in general, we want to do things in general that look like this. dy dx, I'm going to go really loosely, equals p of x, q of y. Not plus, but times. Now, either p or q could end up being quotients. That's not the thing. So what I'm doing is I'm relating two functions as a product. I could also write them as a quotient. Right? If I said a over b, could I write that as a product? Yeah. So if I have two functions and I'm looking at them and they're written as a product or a quotient, because I can always pull that apart, I can solve this using the next technique we're going to learn. And this is the only technique we're going to learn. If that's a sum, this is way, way, way more complicated. That's not even this semester. But if I have something in this form, so the idea is I want to be able to manipulate this and move things around. Now, I only have one independent variable. Okay, x is my independent variable, so ultimately I'm going to integrate with respect to x. But let me remind you, when you're doing substitution, I'm doing the following problem. Oops, sorry, come on, peace. This is the most generic form that we've learned for a U substitution problem. So I have, maybe off to the side, I have something like this. I have 4x cubed minus 3 to the 5th power times 12x squared dx. I can do this because if that's my u, 4x cubed minus 3, then there's its derivative right here, right? I have a function not of x, but of g of x. So in this problem here, we know, and again, I have notes posted in case you forgot, let u be g of x, then its derivative is g prime of x, okay? That's not really a stretch. But now when I'm replacing within my integral, we have to remind ourselves what's the notation. I'm going to do du dx with respect to x, and I know that equals g prime of x integrated with respect to x. That's not really a question. What do I have on the right side? When I integrate this, won't that be g of x? But on the left side, when I'm doing this substitution, I no longer have x's, I only have u's. Mathematically, the integral of du dx integrated with respect to x is the same as integrating with respect to u. Not because they cancel. They don't cancel. This is not a quotient. This is a derivative. This is a function. This is the instruction. I'm integrating with respect to dx. But the result is as if I integrated this entirely by itself. This is what u substitution is. This is the most important thing you probably learned in Calc 1. How do I know that? Well, what's the antiderivative of du? Isn't it u? So now what have I got? U equals g of x, which is exactly what I started with. This is the proof that this and this are the same thing because they both yield this. And the right side is this. So what do we do when we're doing this notation? We do du dx integrated with respect to x is the same as du. Now look at that and look at that. We're saying those are the same. So what we did mathematically, we always wrote it like this. Does this ring a bell? When you did your u substitution, you wrote this. Du is not a quantity. Du is an instruction. Integrate with respect to u. Dx is not a quantity. This is an instruction. What I'm doing is within the integral, and this, by the way, if we don't get this right, we will do things incorrectly in general, and I don't want that. Within my integral, I have an instruction to do g prime of x with respect to x. I'm going to replace this instruction with this instruction at the same time that I change my variable. So this will now become f prime of u, and this part here now is integrate with respect to u. You cannot have x and u in the same integral at the same time. That is impossible mathematically if one of them is independent. It's possible to have two variables in the same integral if they're both independent. That's what you do in Calc 3. All of your integrals have multiple variables at the same time, but that's something completely different, completely unrelated. So when we do a substitution, it's all at once, it's not piecemeal. Anytime you ever have an integral where you have x's and u's in the same integral, it does not equal this. It equals something very, very different, and it is never going to produce the right answer. But I always got it right. No, what you had is 3 or 4 different answers to the same question. That's like circling all the bubbles on the multiple choice and saying, but I got the right answer. No, you have a whole bunch of wrong answers. Many, many years ago, I was teaching a Calc 1 class, and early in the class, first couple weeks, I had a student, and for every single answer to every single question, he would write 0 or 1 or infinity or D and E. That was the answer to every question the first 2 or 3 weeks of class. And he wasn't getting anything right. He goes, but one of those is always the answer. Well, one of those is often the answer, but it's not always. But he would write 0, 1, infinity, or D and E for every single question. He goes, but I got the right answer in there. I said, no, you have a whole bunch of wrong answers. You know, the true false question, let me write true and false. Let me circle both of them, then I definitely have the right answer. No, you have the wrong answer. You can't have multiple answers when there can only be one. Okay, so this is what we do. This is exactly the big theory over here. So the first thing I'm going to do is move the y term over. Remember, that's what we did with the population growth? We moved the y term over. That's what we did with the Newton's law of cooling. So now I'm going to have something of this form. 1 over q of y, dy dx, let me erase this, now equals p of x, and now I'm going to integrate both sides. Let me put it back over here. It's going to get a little bit too messy. Now I'm going to integrate both sides with respect to x. Now I want to show you something. That's ugly, isn't it? So what do I want that to look like? dy dx integrated with respect to x is the same as integrating with respect to y. What do I have on the right side? I have p of x dx. This is the problem I am now solving. Notice on the left side, it's purely a function of y. On the right side, it's purely a function of x. That's a good thing. I don't have x's and y's in the same integral at the same time. That's not actually possible when one is dependent. But now let's go back to the original problem. It's as if I just simply broke it apart, isn't it? Question is, can I go from here literally directly to here? Yeah, actually you can if you can see what's going on. This is what is called a separable differential equation. I am separating the x's and the y's, and I can only do this if x's and y's are related through either a product or a quotient. If they're related any other way, through a sum, through exponents, through a function, can't do it. So, we'll do a couple of these examples. We know how to solve this if we know how to set it up. Do I have a blue? No. Huh, don't look like I have any blue pens. A lot of blue caps. Okay, let's do the following problem. We've got e to the x dy dx equals, how about cosecant y? Now let's throw another distinction here. Let's say that y of 0 is pi over 2. What is this thing here called? I don't need this to answer this question. Anybody know what that's called? It's extra. It's called an initial condition. We did this when, remember, we saw population growth. I said, oh, we have to know, we have the initial population. If I don't give you that, then your final answer is going to have an arbitrary constant in it. The initial condition allows you to solve for the arbitrary constant. This is done last. This is not calculus. This is just so now I can figure out what the value of whatever arbitrary constant I'm going to get is. So now I want to manipulate this. I want to rearrange this. How do I do that? Well, let's start first of all by moving things. Let's move this guy to this side, and let's move this guy to the other side. So if I do that, multiply both sides by the reciprocals. What's the reciprocal of cosecant? Sine. So I have sine y dy dx equals, how about just e to the negative x? Now when I integrate both sides with respect to x, can I write the right side this way? I'm into saving time. I'm okay writing the right side that way? I'm integrating with respect to x. I want to integrate the left side with respect to x. dy. Can I just do that? Can I go that fast? Yeah, I can. I think you actually should. Yes, I can write dy dx, and then rewrite it again with dy, but this is the whole point. I separated this into two problems. Now, is either problem difficult? Either one of these? No, they're pretty simple. I don't know what the final answer is going to be, but I know it's not going to be all that complicated. So, what's the antiderivative of sine y dy? I'll put up here. Negative
Cosine?
cos y. What's the antiderivative of e to the negative x? Negative e to the negative x. Now there should be a plus c or something. Do I put a plus c on both sides?
No.
It is an interesting, if I do this, no, because then my c's will always cancel, won't they? Oh, no, but first of all, each antiderivative should have its own arbitrary constant, meaning any real number is acceptable. Is there any chance they're going to be the same? It's a 1 out of infinity. No. So how if I did this? Okay, now let's throw this on the other side. Now the other side is C2 minus C1. So wouldn't it have been easier if I just did this? Yeah, I only need 1 plus C. Don't do it in stages and then eventually get 1. Just put 1. Does it matter which side I put it on?
No, because positive or negative, there'll still be some constant.
It's still going to be some arbitrary constant. Is it mathematically possible that the constant is 0? Yeah, anything is possible. Never assume, though. Now, I would be done with the calculus except that I gave you an initial condition. So we can actually figure out the value of c. So here's the question. I can solve for y, do an inverse cosine. I can solve for x by doing a natural log. I can put these on the same side. By the way, all forms of the final answer are correct. They are acceptable. But are they all useful? Now, I say this in all seriousness, because how many here right now are in a physics class? Okay, so are we completely done with the problem now? No, you realize you've just done the first step of the problem. There's probably a whole bunch of more steps. If you're in a science class, the math is only one step. It's never going to be the end of the problem. So whatever I just got, I'm probably going to have to use this answer further, right, to do something. So what form of the answer would be the best? Well, am I going to use the value of x later on? Am I going to use the value of y later on? I don't know. The situation kind of dictates what's the best form of the answer. But when you have an initial condition, my suggestion is find it as soon as you can. Don't wait and find it later. Find it now, because it might actually be 0. So how do I find? Well, this says when x is 0, y is pi over 2. That's what that says. So negative cosine of pi over 2 equals negative e to the 0 plus c. What's that?
0.
0.
1. Negative 1.
Negative 1 plus c. Therefore, c is?
Positive 1.
Positive 1. It didn't matter which side I put the c on. If it had been on the other side, it would have been negative 1. So now can I say, aha? So we all say, aha. The answer is going to look like negative cos y equals negative e to the negative x plus 1. Now, do I solve for x? Do I solve for y? Do I put everything together? There are 3 generally considered acceptable forms, and I could care less which one you use, but it's probably not this one. This seems like I'm kind of leaving it unfinished. So the first form, the easiest one, is put x and y on the same side. So e to the negative x minus cos y equals 1. Perfectly good answer. Probably the least useful, because if somewhere along the road I need the value of y or I need the value of x, then I probably should solve for them. Now, when you're told to solve based on this form, which is the dependent, which is the independent? I use dy dx.
dx is independent, dy is
Well, X is independent, Y is dependent, which means that I should write the answer Y equals. It's not wrong to write it X equals, but it's probably more useful to write it Y equals. So I need to get the Y by itself. So the first thing I'm going to do is multiply both sides by what? Negative 1. So then I have cos Y equals e to the negative x minus 1. Therefore, what does Y equal?
Arc cosine?
Inverse cosine. Yeah. Arc cosine is not inverse cosine. If somebody told you that the same thing, they lied. Arc cosine means all values that are coterminal. It means infinitely many. Remember in trig plus k2 pi? Remember doing that? Arc functions give you every single answer. Unless you're using terms like principal arc, which by the way, if you haven't been told that, somebody lied to you. The only reason any human being ever used arc in the last 50 years is because to type that with an exponent of -1 actually was quite difficult until word processors were invented. So therefore, textbooks came into print after the 90s, nobody uses arc anymore. That's like in the 50s and 60s because they actually couldn't type the exponent. That's a terrible reason, but that's actually the reason. No, arc is not inverse. And I don't want to spend too much time in this. The higher you go in math, if you're taking an upper division, complex analysis course, and you use the term arc, they're going to throw out everything you just did, no matter how good it is.
Is it supposed to be -1 for any reason? When I thought C was a positive?
Right, but when we multiplied both sides by -1,
Thank you.
in order to see how I rewrote it here. Now, way back when, and this is, I say this in all seriousness because you're going to run into this in every class. I would like the square root of 1. What are you going to tell me? 1. I want the square roots of 1. What are you going to tell me? Plus or minus 1. I want the fourth root of 1. 1. I want the fourth roots of 1. Plus or minus 1, plus or minus I. You remember doing that? That's de Moivre's theorem. You did that in pre-calc. Oh, yeah. When we say square root singular, we're automatically saying the principal square root. But if I use the plural, then I'm saying all square roots. If I said I want the sine of x to equal, let's say, 0, well, 0, or pi, or negative pi, or 2 pi, or 3 pi. Oh, aren't there an infinite number of answers? So the arc sine of 0 is k pi. The inverse sine of 0 is the one angle between negative pi over 2 and pi over 2. That's called the principal. When you say principal something, then you're talking about one thing where you've restricted the domain. I've never in my life had a class where they used arc, ever. I've never had an instructor in any class, but they always said, I'll mark it wrong if you use it. And I'm talking, a few presidents back. But also at the same time, I've never used it. It's a lazy way for people to answer a question, but it's not a correct answer, unless you're actually going to say principal. Do you know we actually have different notation for principal arc? When you look in the textbook and you see this means there are infinitely many solutions. Everything's coterminal. But if I wanted to use arc correctly, do you know what this is silly. This goes back, I don't know, at least to the last century. You capitalize the A in the arc. That's how you indicate its principal. It seems kind of silly. No, it makes a difference. If I'm saying give me all solutions, do you remember in trig and pre-calc, give me all solutions? Okay, plus k2 pi. Give me all solutions between 0 and pi. Do you remember answers like that where it was restricted? Oh, okay, now it's not infinitely many, now it's probably 1 or 2 or something like that. So I want you to always be right, but I want it to be very clear. If I ask you for the natural log of a number, obviously there's only one answer, right? There's infinitely many. But it's implied when I say natural log that I want the principal natural log. But if I said give me the natural logs, plural, now you got the plus 2k pi thing. Yeah, natural log is one of those. It goes back to Euler's theorem. Remember e to the I theta? Remember that kind of stuff? There are infinitely many solutions to many of the problems, but we often only want one. When we're dealing with square roots, we usually only want one. Well, that's why if we use words like inverse sine, we've already restricted the original domain to guarantee one solution. Now, I don't want that to be an issue, but if you actually were looking it up correctly, how many have ever used Wolfram alpha? I use that to check solutions, but I never use it to integrate. I will do the integral, get an answer, and then I'll use Wolfram to differentiate my complicated answer, and if I get back my original integrand, I know I did it right. If you've ever used Wolfram, I say this jokingly because my DiffyQ class, they've all used it a million times. So you put an integral in Wolfram and you get an answer. Typical, there'll be 7 answers and at least 3 of them will be complex, and none of them will look even similar. No matter what the question was, you're usually going to get about 7 answers. Anybody know what I'm talking about? And you're trying to figure out which was the one I want to use. It might not be any of them because it's giving you so many versions of the same thing. So when I'm doing the problem and I do the integral, you guys are all going to be in this position. You're doing the problems, you got the answer, you got the integral, I got this answer. How do I know if I did it right? Differentiate your answer till you get back the original integrand. If you did, then you did it right. But what if the answer is really complicated? Because after today, it's going to start getting really complicated. Your answers are going to be bigger than the questions. That's where I use technology. I ask technology to differentiate my answer because I'm lazy. See, you're going to learn techniques to integrate, but the check, which is also always the derivative, in most cases will be much longer than the integration was. And I did the integral flawlessly, but because the derivative of that answer was so complicated, I made a mistake on my derivative. That's never going to happen, right? And now I don't trust my final answer, but my final answer was actually correct. So that's where I would use technology. Don't use technology to do the integral. That won't help you any, because you won't recognize the answer most of the time. So there's a second form that these problems come up in, and this is probably the more common form, and that's something of this nature. This is the same question, basically, but it's already been separated. Now, the one thing we like about this question, in this problem here, it's absolutely clear that y is dependent, x is independent. So if I'm writing a final answer, I kind of have to write y equals. Can you tell me which variable is independent and which one is dependent in this picture? Not exactly. But, and this is not from this class, you'll learn this next semester, but the nature of the d's in my dx and dy, the fact that the d's are straight up and down means this is what is called an ordinary derivative. Some of you have heard of a partial derivative. That's what you learn in Calc 3. That's when you have multiple independent variables. It's a completely different symbol mathematically. But the fact that that d is straight up and down means exactly one of these is independent. Only one independent variable. But because I wrote it in that form, what it means in my final answer, it really doesn't matter if I solve for x or I solve for y. You would prefer that. What if the nature of this last problem, what if it was way easier to solve for x? But I'm solving for y because of the way the question was asked. But if it was easier to solve for x, why not solve for x? So in this form, what do? Well, the first thing we do is, I'm going to throw that on the other side. Here's the best part now. I'll go slowly. There. That's how you answer the question. That's kind of nice, huh? This is a separable differential equation because of the x's and y's. You say, well, I thought you said connected through products or quotients. I could multiply both sides by the reciprocal, and then they'd be connected as a quotient, wouldn't they? But not as a sum. So let's do another one of this nature. I have got, let's say, y squared dx plus, how about 1 over x dy equals 0. Keep this one relatively simple. This time I'm not giving you an initial condition, which means there's going to be a c in my final answer. You don't care if there's initial conditions. Initial condition just means there's one more step. There's an arithmetic step. Not having initial conditions actually means there's less work. But it means my final answer has the arbitrary constant. So can I just integrate both sides? Let's start by moving things around. Okay, so can I now just go ahead and integrate both sides? I'm winking. Oh, those in my class, you know that. If I'm winking with my left eye, there's something. Can I integrate both sides? Why not? You were shaking your head. Why not?
Because the dx and dy.
Yeah, I got the x's and y's in the wrong place. Oh, well, that means I can't do this. Or can I move things? Yeah. So let's multiply both sides by 1 over y squared, and let's multiply both sides by negative x. Does it matter which side the negative's on? Actually, let's multiply both sides by positive x. And let's multiply both sides. How about not 1 over y squared? How about y to the negative 2? Sorry, this is it. There we go. Is this correct? Algebraically, even if you didn't know what calculus was.
Yeah.
Algebraically, you okay with that?
Yeah.
Yeah. So now I can do that. Well, let's see. On the left side, I'm integrating x dx. I'm pretty sure I can handle that one. What's that going to be?
1/2 x squared.
1/2 x squared. And on the right side, I'm integrating negative y to the negative 2.
Negative 1 over.
That's why I left the negative on the right.
Y.
So it'll be positive,
Y.
positive y.
Y to the negative
Y to
3 over
negative
3.
one.
Add 1 to the
Y to the
exponent.
negative 1.
Positive y to the negative 1. Could I write it as 1 over y? It doesn't matter, but that's it. Yeah, that's it. I'm done with the calculus. Now, I would like to solve for one of the variables. Which variable will be easier to solve for?
1 over
X.
y.
The x presents a little bit of a problem. Why? WHY.
Because it's
Squared.
It's
squared.
being
and then you
squared,
can
which means I got to deal with plus or minus square roots. I think y would be better. Do you agree? Now, could I just move everything to the same side?
Yeah.
Would it be legal for me to do this? Yes, but that may not be the most useful. And many of you heard me say this before, and you're going to hear me say this a lot. It has nothing to do now at this point. It has nothing to do with being right or wrong. It has to do with what is the most useful form of your answer. And I can't answer that because it depended on the situation in the first place. But I want to make sure you understand there's multiple correct versions of the answer. It's not wrong if you have a different version. Okay, so it's probably the case that solving for one of the variables is easier. But in this case, because the x is being squared, I think we're safer getting the y. So first thing I'm going to do is get the y by itself. Let me call that one C1. Because now I'm going to throw it on the other side. Check this out. I can't say plus C1 because I just threw it on the other side. It'd have to be minus C1. But if C1 represents any real number, then negative C1 is just a different real number. So now what do I do?
Inverse it, like reverse it.
Yeah, reciprocal. So far, so good? Everything I've said is true and correct. Would we consider this to be a simplified answer?
No,
What don't you like, Cece?
it's not the fraction.
The fraction, yeah. And by the way, there's nothing wrong with this, but generally speaking, we don't like fractions within our quotient. So I did this on purpose. So, easiest way to do this, just go like that. So now what's my final answer? My bestest, well, 2 over x squared plus 2 times c2, and what's twice an arbitrary constant? Just another arbitrary constant. You like that? Yes, you can keep doing that. Every time you change your arbitrary constant, you just rename it. But to say my answer is going to be, negative 1/3 of c squared minus 4, it's an arbitrary constant. So this would be probably the best version of the answer. Least amount of work to do. Yeah.
If you had a initial condition,
If you had an initial condition.
you have to keep all the times 2 and stuff like that.
Okay, if I had an initial condition, really the question is where should I could do it now. What if it turned out that C was 0?
Oh, then you don't.
I've been carrying this all the way through and changing it only to find out later. No, I would do the very first opportunity you have to find the C, find it. And then when you double it or multiply by -1, it's easier to keep track anyway. If you have an arbitrary constant, it shows up in the answer. If you have an initial condition, find the value of the constant as soon as you can. There's no advantage to waiting till later. It never makes it easier. but it can actually make it more complicated. So if I had given you some initial condition, you know, y of something equals something, you'd plug it in right here. And then solve for y, and in the end, you're going to have plus a number, or potentially that could actually be 0. Never assume it's 0. That would be dangerous, because most of the time it won't be 0. Okay, any questions so far? This is a separable differential equation. This is how we solve them. It's pretty simple to recognize. But I'm integrating an x dx term, I'm integrating a y dy term. Now, where do we use this kind of stuff? Well, technically, we did a version of this last day. We just did simpler versions. We did the population growth, we did the Newton's law of cooling. But just within those problems, I really didn't see both variables showing up. So now we're going to do one of the coolest applications, I think, of this. We're going to do something called orthogonal trajectories. Now, there's a word in here that you need to know, a very important math word, orthogonal. And a lot of you may not be familiar with that word. I've said it many times. If we're doing something in class and you're following along okay, and then I use a word that you're not familiar with, we're done, aren't we? Everything's now gone because I have no idea what you're talking about because I don't know what that word meant. Orthogonal is one of the more important math words. In fact, it's a geometric word, but it's used in Calc 3 all the time. I mean, most lectures we're going to talk about orthogonal. There's another word that's very similar to orthogonal. It's the word I want you to think of. When you hear orthogonal, what's another word that mostly means the same thing? Does anyone know?
Perpendicular.
Perpendicular. So why don't we just say perpendicular? Because perpendicular has very strict rules. Do you see any perpendiculars on the ceiling? Yeah, you see lots of. You see these lines crisscrossing. I think they're at right angles. That's what perpendicular means. Do you see any perpendicular walls in here? Yeah, and all of those would be orthogonal. There's nothing. So if you're thinking perpendicular and orthogonal, you kind of put them into the same. Yeah, if it's perpendicular, it's definitely orthogonal. But orthogonal doesn't necessarily mean perpendicular. You can only measure angles between straight things. In other words, only between lines and planes. You can't measure an angle between curves. That doesn't have any meaning. But what if the tangent line what if those two tangent lines were perpendicular? Then we would say the curves are orthogonal. Orthogonal is bigger than perpendicular. Anything perpendicular is orthogonal, but orthogonal doesn't necessarily have to do with straight. Okay, now use the simplest one, because this is the one we use most in Calc 3, because we do 3 dimensions. I got a basketball. Okay? Anybody ever pump up a basketball? You stick the little thing in the, okay? Imagine from the center of the basketball, I'll draw a picture of it. Because I need you guys to understand and have a very thorough picture of orthogonal, because nothing we do is going to involve lines in that sense, okay? Yes, I can do circles and spheres. I can't do line segments, but okay. Center of my basketball. I want it to come straight out of the basketball. Doesn't matter where it's going at. It's going straight out of the basketball. My basketball is a sphere. I've got this ray coming straight out of the basketball. So that ray would be like me standing on the floor. I'm on the surface of the basketball and I'm this ray. The surface of the basketball is not flat. But if I took a piece of cardboard, something stiff, and I put it on the basketball, don't press down. If I put this stiff piece of cardboard on my basketball, then in theory, how many points does my cardboard make contact with the basketball?
1.
Technically at 1. If I push it down, mash it, and curve it, no. If it's perfectly straight, in theory, only touching at 1 point. Now, that line coming out of the basketball is absolutely perpendicular to that plane, isn't it? So therefore, the line, or the ray coming out of the basketball is orthogonal to the surface of the basketball. It's not perpendicular because the basketball is not flat, but it's perpendicular to what's called the tangent plane. We spend a lot of time in these. No, not counting this classroom, I am clearly perpendicular to the floor. That's not a question. So I need you to go to the beach for this one. I need you to go to a park for this one. I need you to go to some place where there's no engineered floor. I need you to stand on the surface of the earth. Are you orthogonal to the surface of the earth? She's got no lead. No, you're orthogonal to the surface of the earth. Are you perpendicular to the surface of the earth? No, because unlike Kyrie Irving, we know the earth is not.
Flat.
He's the basketball player who actually apparently believes the earth is flat. He went to Duke. That's the weirdest part. No, the earth is not flat. The earth is essentially spherical. I don't say that jokingly. So you're not perpendicular to the ground, but you are orthogonal to the ground because it's not flat. I'm saying you can't be in here because this was engineered to be flat. Orthogonal, therefore, has to do with perpendicular. We're going to look at things that are orthogonal, but they're going to be curves. That's why. Now, what's a word that goes with perpendicular geometrically? There's another word. Look at the ceiling. You see something else going on. Parallel. Parallel, orthogonal and perpendicular, they go together. But remember, curves can be orthogonal, because their tangent lines are perpendicular. I can be orthogonal to a surface if I'm perpendicular to the tangent plane. That kind of makes it easier to conceptualize. But parallel is one that we get wrong because we have done math our entire lives only in 2 dimensions. So if I ask an educated person, what does it mean to be parallel? They're going to say, oh, it's any 2 lines that don't
Cross.
or intersect. So take any line running along the ceiling, take any line running along the floor. They're not going to ever intersect, are they? Are they parallel? No. Probability of 0. Take any 2 planes leaving San Diego Airport. Are their flight patterns going to cross? And by the way, this is not a joke. This is an absolute.
No.
It's not possible. Well, okay. We can't intentionally have flight patterns cross because if flight patterns cross, what do we potentially have? Mid-air collision. So no flight patterns cross yet. All planes aren't going to the same destination. Therefore, my destinations are not parallel. Parallel, no. If things are parallel, they're not going to intersect. Not intersecting has nothing, 0 to do with parallel. You're in 3D. These are called skew. Anything running along the ceiling, regardless of the direction, anything running along the floor, regardless of the direction, they're never going to intersect because the planes were parallel. But if I'm in the air, no. So parallel actually has 3 things if any 2 of them are true. So never intersecting, that's a good one. Now, go back to baby algebra lines on the plane. So if they're lines and they have the same slope, okay? But now, think something simple. My simplest example I like to use are railroad tracks. There's 3 aspects of parallel. Non-intersecting, same direction, and equidistant. If any 2 of those 3 are correct, then you have parallel. But the non-intersecting is not nearly enough because that doesn't imply same direction. So think of railroad tracks. Would you say they're non-intersecting?
Yeah.
Would you say they're equidistant? Yeah, that would be a problem if they weren't, right? It'd be hard for the train. And are they going in the same direction? The railroad tracks? Hopefully they're going in the same direction. It's not like... Now, did anyone drive on the freeway today? Did you deal with parallel? Yes, you did. Give me an example of parallel.
Lanes.
Your lanes. You are bounded by markings on the road. Did they stay equidistant? Did your lane become narrower or wider? Probably not. Are they going in the same direction? I hope so. And do those markings ever intersect? Probably not. Oh, by the way, are your lanes straight?
No.
No. Parallel has nothing to do with straight. If it's straight, it's easier to describe parallel. Parallel has nothing to do with straight. That's what I'm saying. Most people have an incorrect interpretation of parallel. Parallel, non-intersecting, same direction, equidistant. Your lanes on the freeway are parallel. Oh, and you're in 3 dimensions. Now, when we go back to baby algebra and we're only talking about lines on the plane, now I just need 2 lines with the same slope but non-intersecting. I still had to have 2 things. To say same slope, they could have been the same line. Now, we're in 3D, we talk about planes a lot more than we do lines in 3D. So I have these two planes, they're infinite, they're never going to intersect, they're going to be parallel, they're equidistant, all those things. Parallel, we want to have a good concept of. Now, we don't use that one so much in this class. We use that one a lot more next semester. But again, I don't have to be straight. But if I am straight, like lines and planes, then parallel and perpendicular are much easier to conceptualize. But now you have to think that I don't have to be either one. So what I've got now, here's what we're going to do. Orthogonal trajectories. Let's consider the candelabra of parabolas. Remember we did this last day. So, I don't know what color this is. So what I want to do is draw a whole bunch of parabolas that satisfy this equation. You know, this is called, we said, a family of curves. What I would like to do is come up with another family of curves that at every point of intersection is orthogonal to one of these. Now, if I just drew a line, it's probably, I could make a line orthogonal to one of them, but that same line probably wouldn't be orthogonal to all of them. Might only, probably only be orthogonal to one. So orthogonal trajectories would be another set of curves that every single curve that I draw, this is infinitely many, I have another set, infinitely many, and they're all orthogonal. Well, that's crazy. Now go back to baby algebra for a moment. If I told you the slope of a line, and I asked you for a line that was perpendicular, assuming it's not vertical or horizontal. If I gave you a line of slope, of slope m, let's keep it simple. Then a perpendicular line, what would the slope of my perpendicular line have to be?
Reciprocal and opposite.
Give me a value.
Negative 1 over
Negative 1 over
m.
m. Because remember, the product of the slopes of perpendicular lines must be negative 1. Now I said that's excluding vertical and horizontal because there'd be a 0 in there somewhere. Okay, excluding those guys. Could you tell me the slope of the tangent line at every point on this graph? Yes, you can. The slope of the tangent line. That's what dy dx we will measure. That's our first introduction to a derivative, was the slope of the tangent line. What is dy dx in this case?
2x.
2x. So every single one of these curves, the slope of the tangent line is 2x. What I need is another set of curves where the slope of the tangent line is this. So, what dy dx do I want to use for my new problem? If those slopes are all 2x, I want a set of slopes that are orthogonal, or think perpendicular.
1 over x.
Negative half x.
dx dy.
Negative 1 over 2x.
There we go. Same thing. You just did this. You said, let me take the negative reciprocal. Everybody okay with that?
Yep.
If that's the set of slopes for that group of curves, then this should be the set of slopes for this group of curves. Now, I would like you to solve this differential equation. Is this a differential equation? It most certainly is. Is this a separable differential equation? Yeah. What don't I have? I don't have any y terms. That makes it even easier, by the way. Oh, okay. So for me to solve this, then aren't I just saying the integral of dy equals the integral of negative 1 over 2x dx?
Yes.
So on the left side, I have a y. Now the negative, well, it's not the negative, it's the 2 probably bothers a lot of us. If this bothers you, then do this. That might make it easier. A lot of us make the mistake of our eyes going to the coefficient. Coefficient has nothing to do with the antiderivative. This antiderivative is going to be what? Well, it's going to be a log, isn't it? That had nothing to do with the negative half. It's going to be a logarithm. Oh, the negative half's just the coefficient. So what's this?
Negative 1 over 2 ln absolute value of x.
I definitely need absolute value. Not putting the absolute value would drastically change your answer. Now plus, well, we had a plus C over there, so maybe we'll call it, I don't know, we'll call it C1. Call it a different C. Because this C has nothing to do with that C. Ooh, that's a bunch of ugly looking curves. Why do I need the absolute value of x? Well, if you remember back in Calc 1, the reason you had the absolute value is, think domains for a moment. If I said I'm thinking of a function with a particular domain, when you take the derivative of a function, your domain cannot change except if you have endpoints. So something like the square root function, there's an endpoint, right? 0. But the derivative of the square root is defined everywhere. For positive numbers, it's not defined at the endpoint because you're not differentiable at an endpoint. If my original function was defined for all real numbers, then my derivative is probably defined for all real numbers. The exception would be if something ends up in a denominator, right? Okay, like cube root function. I'm not differentiable at 0. So when you're taking a derivative, the most you can lose is literally one value. Your domain stays the same. But when you're doing an antiderivative, can you lose the domain? You're never going to gain a domain, but you can't lose a domain taking an antiderivative. Go back to my original question. Can't I use any real number for x there?
You can.
And my slopes now? So, I can use any real number except 0, but now look at my antiderivative. If I don't have the absolute value, now I've restricted this to only positive x's. I can have negative x's in this statement. There's no wrong, I just can't have 0. Oh, so the absolute value is so we don't lose half of our number line, we don't lose half of our domain. Because there's nothing wrong with having a negative x. Now let's just concentrate on the log for a moment. What does a logarithmic graph look like? Well, it's this guy, right? What would the log of absolute value of x look like?
You have another one on the other,
Flip.
Reflected across the y-axis.
Good, good. It would look like that. So that'd be log x for positive x's. This would be log negative x, if you will, for negative values of x. That's where the absolute value comes in. Now, what if I want the negative of the log of x? What does a negative do to any graph?
Flips it.
Flips it upside down. So now if I want the negative, it's this graph, but now it's going which way? It's going like that. And this graph is going like that. You agree?
Mm-hmm.
So now if I consider every possible plus c, what am I doing with these curves? I'm moving them up, I'm moving them down. Huh, wonder what that would look like. Okay, if you don't think that's cool, if I draw every infinite of those at every point of intersection, I'm going to have orthogonal curves. Isn't that cool? So the family of curves that are orthogonal to my candelabra of parabolas is a bunch of logarithms, but all upside down logarithms. That's interesting. If nothing else, it's cool. Now, do we use this? Yeah, we use this for all sorts of different things. But, okay, a lot of you haven't been in my classes, so you don't know. I like to take things that you are familiar with in real life, whether it be stories, whether it be movies, and show how the calculus has been applied. I mean, if you were in my class, you learned, right, the quotient rule, of course you learned, because Snow White and the 7 vertically challenged engineers who would sing it every day to work, ho-de-hi, minus hi-de-ho, all over, ho-ho. That's how they learned the quotient rule. I tell the story of the lost island of Sokotoa. Right? Krakatoa disappeared off planet Earth after the largest known tsunami ever hit the Earth in the 1800s. Well, the sister island of Krakatoa went with it. It's like the lost city of Atlantis down there. They were doing large trigonometry problems without any form of technology because, well, it depends how you spell Sokotoa, right? So I like to use that. Calc 1, I could not prove the fundamental theorem of calculus without using the garbage pit scene from the original Star Wars movie. Remember, as the walls are closing in, that's how we actually prove fundamental theorem, by showing how the delta z is approaching 0. Well, I cannot do calculus 3 with multiple independent variables without introducing the cat in the hat, because of course, Poor's assistants. Thing 1 and thing 2, those represent independent variables. And if you actually read it, you go, my God, it's all calculus. Today, one of the major problems we're going to look at today, we're going to involve the third Indiana Jones movie, the one where they have the knight and the thing, and then drinking the goblet and all that stuff. I can't prove it without using that. This stuff is really cool. Okay. Star Wars, second Star Wars movie. You guys remember when Han Solo and the Millennium Falcon, they were kind of like glued to Darth Vader's ship? And remember when they released the garbage, they sort of trickled out. Remember, they sort of floated into space and they got away for a while? Well, Darth Vader's in his little big chamber, iron lung thing. And the guy comes in and says, we've lost them. And he says, find them. Some version of that. And he says, well, they're in an asteroid field. And they say, remember, asteroid fields do not concern me, Commander. Set a course on their last known trajectory. In other words, Darth Vader is explaining exactly what's going on here. The word trajectory has to do with tangent lines. That's not a joke. A trajectory is straight. In differential equations, one of the major problems we do when we do a problem later called Euler's method, we use this concept. It's exactly how they do search and rescues out in the ocean. From last known coordinates, last known position, we extend and say, if we continued, where would we end up, even if we're moving on a curve? Otherwise, right, we wouldn't be able to find people who are lost out at sea. It actually is a very effective way. So the trajectory is where something is going. Okay? These are orthogonal trajectories. But a trajectory would involve a tangent line and you continue in that direction. So why would we use a tangent line? Okay, if you're in your car and you hit a slick spot on the road, do you slide in a curve? If you were driving in a curve, do you slide in a curve? I've got the yo-yo on the end of the string and I let go of it. Does it continue flying in space in a curve? No. What direction does it fly? What direction do you slide?
Straight.
But in what direction? Very specifically,
Point.
when you're on that curve, you're on the windy road and you hit the slick spot right here. Aren't you going to slide that way? You will always slide in what direction? I'm looking for a word. In a direction that is tangent to the direction you were going. This is huge in Calc 3 when we talk about motion. You can only slide in a tangent direction. Your trajectory will always be in a tangent direction. That's an absolute. That's basic physics right there. So an orthogonal trajectory means I'm doing the same thing. I'm involving tangent lines, but I want all of my tangent lines, infinitely many, to be orthogonal. That's kind of a cool application. Okay, I'm just showing you one. We could do this for most curves. I don't want it to be inconvenient. The key was just using this to get the orthogonal part. And you notice we weren't talking about lines. We said that tangent lines are orthogonal. That's what made the curves orthogonal. Okay? Because there's no angles necessarily. Now we're going to go on to the next thing. Now this is the first of the methods of integration. So for the next couple weeks, our major theme is on what are called methods of integration. If a problem looks like this, you attack it this way. Calc 1, you have about 20 antiderivative formulas. If the problem looks exactly like this, then the antiderivative is this. There is no work in between. But sometimes, okay, there is no antiderivative formula that looks exactly like this because my argument in this case is not an x. All of our antiderivative formulas are if the argument is just something simple. I have my argument as a function. It's x squared. So according to the u substitution, I need the chain rule factor, which in this case would be what? 2x. I need a 2x. Have I changed the problem when I did this? Or is it the same problem? So if I were to rewrite this, this would be cosine u du. What is the antiderivative of the cosine of u? The sine of u. Yes, it actually is possible to do that directly if you recognize that. All of us hopefully would probably do this. This is wise. I have a formula that looks exactly like that. And we have about 20 of them. If it looks like that, the answer's in the next step. Life is good. What are we doing in this class? Every problem that doesn't look like the formula. Not all things are going to be one step and out. Sometimes we have to apply technique. Okay? So let's remind ourselves, what is the product rule? Now I want to do it formally. I have the derivative of u of x, v of x. I'm going to be real generic. Let's assume u and v are functions, they're not just x. Okay, it might be sine x, it might be e to the x, something simple. I want the derivative of the product. Now what we often do, and this confuses people at first, Because most textbooks will do it like this. Did I just say something completely different when I wrote that? It's very important that we know this. Did I just say the same thing, or did I say something different?
You just said something different.
That's the ambiguity. So here's what you absolutely, first of all, U and V are not numbers, they're variables. It may be the case that I'm saying, no, U and V represent constants. You know, when you see a plus C, you're thinking constant, you're not thinking variable. If I said, no, U and V are functions, this means there is exactly one independent variable in this problem. It's X. That means every other variable you see absolutely automatically is a function of X. There cannot be anything else. Mathematically speaking, there are no other possibilities. Can't be a function of Y, can't be a function of anything else. Why? Because X is the only independent variable. There's different notation involved. And you learn that next semester. I'm not going to bring it up and just confuse. Next semester, you're going to learn what to do when there's more than one independent variable, because we're going to be in 3 dimensions most of the time. But right now, there can only be one independent variable, and the d dx says it's X. So when I write u of x, v of x, that makes it simple. If I write u and v, then it's absolutely automatic that u and v both are functions of x, because they can't be anything else. But a lot of textbooks will just go to this, when maybe at first this would have been better so you're not confused. But I want you to understand this is saying exactly the same thing, because it can't be anything else. And why do we write that way? Because we're math people, we're lazy. You know, I don't want to write of. When you write y, isn't it always y as a function of x every time you use y? Does anybody ever write that? Nobody writes that. When you see y, you know it's a function of x. But if I wrote it that way, there's no confusion. But none of us write that. We just write it as a y. It's understood it's a function of x because I'm integrating and differentiating with respect to x. So if I write it in this form, it's not different. But now let's apply the product rule. Product rule is first times the derivative of the second plus the second times the derivative of the first. We all agree with that? Okay, great. Now, I want to integrate both sides. Oops, sorry. I'll write it this way. I'm going to integrate both sides. Are you okay with that statement? If I integrate the derivative, don't I get back the original function? There won't be any plus c's until I actually finish the right side, so don't worry about the plus c's. Everybody okay with that? If the derivative of u times v is this, then the antiderivative of this should be u times v. Okay. Huh. Look at the notation. Well, first thing is, isn't the integral of a sum the sum of the integrals? Is this a true statement mathematically? I'm not trying to trick you. I have the integral of a sum as the sum of the integrals. But wait a minute. I've got the u dv. Oh, I know what to do. Isn't that just u dv, based on what we learned substitution, plus what's over here? v du. Huh. This is simply the product rule in reverse. There's no question about it. This is the product rule in reverse. Well, let me throw you a what if. What if I asked you a question where you could look at the question and say, well, you know, this is basically the form of the question, and I can't integrate it. We'll do that in just a moment. In other words, in a moment, I'm going to ask you this one. Start with something relatively simple. Can any of us integrate this? No, it doesn't look like any of our formulas. And there's no substitution because my argument is just an x. I don't know what this is. I've asked you something in this form. What if I know how to do this one? Based on whatever u and v represent, I don't know how to do this one, but I do know how to do this one. What if that was possible? Then would it be true that u dv would equal uv minus the integral of v du? Would that be true? Throwing that to the other side. Mm-hmm. Yeah, it turns out of all the techniques you'll ever learn in your life, This one's at the top. This one you will use. This is called integration by parts. What integration by parts means is I give you the integral of a product. In your set of antiderivatives, you don't have products in general, right? You have single terms. And then you integrate them because they were the derivative of something you knew. But you don't know anything that looks like x times sine x, for example. If I throw an e to the x or a cosine, you don't know what that is. But if I'm looking at this problem and I see it this way, if I redo it like this, I might be able to do this one. You with me on that? So we're going to go through a few of these. In fact, how big is this? Well, we're going to spend half of next day on this also. There's so many versions, and there are some very, very challenging problems. So let's start with that problem right there. Now, here's a simple rule of thumb. Whichever one I'm calling dv, I have to be able to integrate it to tell you what v is. Whichever one I'm calling u, I'm going to simply differentiate it. Do I know the derivative and the antiderivative of both of these? So in a sense, it really doesn't matter which one I call u and which one I call the dv. It actually won't matter. I can still perform the problem. So let's start. All right, let's suppose we say, all right, I'm going to start the problem by saying, let me let u equal the sine of x, and the dv will be x dx. Remember, it's implied that everything's a function of x. Well, if that's the case, then what would du be?
Cosine x.
Cos x dx, and what would the v be?
Dx. 1 dx.
I'm integrating.
Oh,
I'm integrating.
oh, right, sorry.
One you're differentiating, the other one you're integrating.
X squared over 2.
So half x, okay? Don't worry about plus c's, they don't come till the very end of the problem. Everything I said is true and correct. So, going back to this problem here, which is way over here. All right, based on what I just said, this is equal to uv, which would be 1/2 x squared sine x minus the integral of v du, which would be 1/2 x squared cos x dx. I'm giving you the absolute money back guarantee that my original question is equal to this. This is correct. Is this an improvement? Why is this not an improvement? Well, I still don't know the answer. And I just went from x to x squared. Do you think that made it easier? No. Oh, man. Now, this is very important. I was actually thinking about doing this earlier, and I got kind of sidetracked in my office, so I didn't. I was going to bring up something on YouTube, but it's going to take a few minutes, so I won't. Okay, third Indiana Jones movie. You guys remember that one? I love that one. That's the one. Remember, he's got to go through all the obstacles, and he's going to cross that long chasm, but there's no bridge, and he takes the step of faith, and it turns out the rocks are just a typical, it's something where there's rocks there, but you can't tell. It's kind of an optical illusion. You guys remember that one? Oh, it's a classic movie. So he gets to the other side, and it's supposed to be the Holy Grail. That's what he's finding. And that's the Petra. Anybody ever seen the city of Petra? I think it's in Jordan. I have a friend who honeymooned there. That's the one with it's got the door that's like 100 feet high, carved into the side of the mountain. Very cool stuff going on there. So Indiana Jones gets there, and the knight who's like 700 years old, he's there. And of course the evil guy who was working with the Nazis. Nazis are always involved in Indiana Jones movies, remember? And he's got the whole bunch of chalices. You guys remember that now? Mm-hmm. And he's trying to figure out which one's the Holy Grail. And the guy goes up and he grabs the one and he drinks it. And like in every good Indiana Jones movie, his head melts and shrivels up, dies. Well, what you didn't realize is right behind him is a big old chalkboard. And they're doing a calculus problem on the chalkboard. They're doing an integration by parts problem. Go back, look at the movie. It's kind of small, so you might not see it. And he's doing an integration by parts problem. Go back to the beginning. I said we know the derivative and antiderivative to both of these. Therefore, I could have made this selection either way. I could have made that my u, or I could have made that my u. But usually only one of those will work. One won't work. This made it harder. So what does the knight say to the guy after he shriveled up? Do you guys remember? He chose poorly. What did we do in this problem? We chose poorly. That doesn't mean we can't do this problem. That means we have to change our choice. Meaning, I'm going to pick u to be the other variable. When you do an integration by parts problem and it doesn't work, it doesn't mean you did it wrong. It means you chose poorly. But fix it quickly so that you don't do the whole Indiana Jones thing, your head shrivels up, right, melts and all that. If you're not sure, go back and look and say, yeah, that seems like quite a penalty for getting an integral incorrect. I'll just mark you wrong, by the way. I won't have your head shrivel up and melt and all that stuff. That's very below average. Okay, so let's change the problem and say, why don't we let u equal x and dv be the sine of x dx? In that case, what will du be? It'll just be 1 dx, won't it? And then what will the v be?
Negative cosine x.
Now, we like this one because du got smaller, not, this didn't get bigger. So now, what is u times v? So my original problem, I'll write it here so I don't have to walk all the way over there. It's uv minus the integral of v du. Minus the integral of this times this, so that will be plus cos x dx. Do you agree? Now, what did I do to my original problem? I just made it a heck of a lot easier because now what am I going to integrate? Just the cosine function. Okay? So what is this?
Sine,
Plus sign?
yeah.
And I'm going to claim this is the answer. I'm pretty sure I did it right. Okay? I'm pretty sure. I'm pretty sure that 10-story building that I put in my backyard isn't going to fall down. I'm pretty sure when I did all my neighbors' taxes and just made up the numbers are not going to get audited. And of course, I'm pretty sure that stray dog that I'm about to pet doesn't bite. You can't be pretty sure in math. You have to be absolutely certain. How can I ever be certain that my antiderivative is correct? Take the derivative. Yeah. Is it possible that there's an error in here somewhere? By the way, what is the most likely error? What's the most likely error when I'm doing trig stuff?
Sine.
Plus or minus errors. Yeah, I mean, is it possible that somebody made an error? Well, you didn't, but the person immediately to your left, they always mess that one up. So, I'm going to go like this. All right. First times the derivative of second, negative x times the derivative of the cosine, that'd be negative sine, plus the cosine times the derivative of negative x, and then the derivative of sine, well, let's see, that's negative cosine plus cosine, so this is x sine x. Is that a good thing? That's my original integrand. Yeah, that's the only check there is. This is the part where I said if you really want to be lazy, yeah, you could check it using technology. That check's easy enough, but sometimes the check can be long, you know. So what integration by parts is meant for is that I'm asking you the integration of a product, and that's not something we already know. If I break it apart, I may be able to do it. It's not an absolute, but it's going to be a vast majority of the time. So this is the first and probably the most important and certainly the most used of all the integration techniques you're going to learn. Any questions so far? We're going to do a few, don't worry. Okay. You know, I need to, I lack dark implements. Here's one. All right, do we know anything that looks like this? Does this look like a formula that we learned in Calc 1? No, because it's written as a product once again. Now, can I integrate and differentiate both of these? Yeah, so technically either one of them could be called my u. But like the last problem, I think you realize if one of them is polynomial-ish and the other one is transcendental, which in this case might be easier to call the polynomial-ish one the u, because then the derivative makes it of a smaller degree. That's the direction I think we'd be better off going. So rather than do it incorrectly and come back, you'll figure out really quickly what the best route usually is. So if I call my ux squared and my dv e to the x dx, then what is my du?
2x.
It's 2x dx, and I do net because that's what's going in the integral, and my v would be
U to the x.
e to the x. Yeah, that's your favorite question, right, in calculus? What's the integral of e to the x? So, what do we got? We got uv minus the integral of v du. So minus 2x e to the x dx. Now, every single calculus book ever written has something in the back of the book called a table of integrals. How many have ever seen that before? Most books, it's about 50, 60 integrals. I have one that I produce for Calc 2. We really don't use it anymore. We used to use it all the time. But the advances in technology have made it a little bit on the obsolete side. But in a table of integrals in a typical calculus book, the majority of all the integrals, they're done badly. They're actually not worthwhile. They might have 100 of them, but only really maybe 30 antiderivative formulas, and 20 of them the ones you already know. Almost every problem, if you have a physical book, look at the table of integrals. The answer to your integral will be another integral, which means it's what's called a recursive definition. And in a lot of cases, it's an infinite loop. It means you'll go forever and never be able to actually get an answer. That's not valuable. Did we do something wrong because my answer's still an integral? Yeah, but tell me about my new integral.
You have to go again.
It's better than the other one. I'm going to go again. There are many problems where you might have to do it more than once, as long as the problem appears to be getting easier. So we're going to do it again, but now we're going to do this problem, not the one. I don't care about that side. I just want to do this problem. So now in my new problem, I'm going to let u equal what?
2x.
And then the dv is,
2dx.
well, if I call that the 2x, how about just e to the x? Then what's my du?
2dx.
2dx and my v. So follow me here. This ain't going nowhere. Now tell me about this integral. It's going to be uv minus the integral of v du Everybody cool with that? Do I have an integral that's simple at this point? Yes, which means I should be able to be done. Now be careful. You are distributing a negative there. So my final answer is going to be x squared e to the x minus 2x e to the x plus, well, what's the antiderivative of 2e to the x?
2e to the x.
2e to the x, good. And we're done. Cool. Now, let's say you're using this in a physics class and you got your calculator out, and you know that entering e to the x on a calculator is one of the big headaches, because a lot of times your e is a second function and you got, it's a little bit of effort. This is an absolutely correct answer. In Calc 1, you are told in every derivative problem, I will put it on the instruction for the first couple of weeks. Every time you take a derivative, I'll say, factor it if it's possible. You guys remember doing that? You absolutely, without exception, if you can factor your derivative, you always factor your derivative. Because what's the only thing you're ever going to do with that derivative? Find out where it equals 0. Yeah, you want to know where it's positive and negative, but you can't answer that until you know where it equals 0. And if you have something that's a big long sum but not in factored form, you're not going to be able to determine when it's 0. So you always factored your derivative, because where it equals 0 is the most important thing you're going to find. So you just got used to it. So after a while, you stop being told that one. Do you ever need to factor an antiderivative? Well, first of all, the plus c means there's an infinite number of possible final answers. Don't worry about the plus c. But you're never going to set an antiderivative equal to 0. There's no application whatsoever to that. An antiderivative probably is never going to equal 0. So there's never a reason to factor your antiderivative. Look at my final answer. You're in physics, and now you got to use this, and you got to evaluate. I'm going to give you 30 different values of x. This is physics, right? I remember doing this back when I was in physics. You guys remember Pinewood Derby? Anybody here ever like a Cub Scout? You got the little wooden block that you carved out, and you did the best you could, and you painted it. It looked terrible, and then every other kid looked like it was professionally done because Dad did it for them. Yeah, it always used to make me angry. Anyway, it's like the projects when you're in elementary school. The kids did it, and you could always tell which ones the parents did. You know, because it looks like they paid a lot of money to have professionally done. You know, when you're in third grade, it probably shouldn't look professional. So the Pinewood Derby, and you put it in, and you're doing down the ramp, and in physics, you're figuring out the velocity maybe every 1/10 of a second, and you're doing like 30 iterations. That's typical physics stuff, even in high school. You've got to enter something over and over and over and over again. So the formula or the function you're entering it in, you'd really like it to be as concise as possible. You're in physics. I need you to evaluate this at many different values of x. That's a lot of button pushing. Can I make this easier on myself?
Yeah.
This is kind of the oh-duh. Do you see anything that might make it easier?
Factoring it out, so I do e to the x and then parentheses x.
Can I write this as x squared minus 2x plus 2 all times e to the x? Now don't worry about the plus c, because if this were an application problem, this would be a definite integral. So you wouldn't have to worry about the plus c, but you're going to evaluate it. Why do I like this better?
Easier to enter into calculator.
Yeah, I've only got e to the x one time, not 3 times.
And also we've got a parabola,
Yeah, that might be. By the way, remember I said you're probably never going to set it equal to 0, but for the ease of evaluating,
We don't need e to the x because we can find 0 without it.
no, you're never going to set an antiderivative equal to 0. That's actually never going to happen in your lifetime. I looked. I checked all the possible roads you might take. No, I'm not aware that there exists or ever will exist an application where your antiderivative is 0. That'd be like saying the area under the curve I need to be 0. That's not going to happen. Don't worry about it. There's less e to the x's. This is the answer. But if we're in another class where I have to use that answer, don't we agree that that might be a little bit easier to manipulate? Oh, besides, I want you to check it through differentiation. This makes it really easy. Exactly 1/3 as many steps. You got to do, how many times you got to do product rule on this one? 3 times. How about on this one? Once. Yeah, I think I'd rather check that answer. You never have to factor. But it makes perfect sense to factor that one because it would be way more useful. You got it? You never have to factor. But it would make sense. And that, so if you were looking at a solution, it's probably in the factored form just because it's easier to work with. But this is the answer. Make sure we understand. You don't have to keep going. So in this case here, we chose the u to be the polynomial term, which made perfect sense because it got easier as we went. The rule of thumb is always the same. If you can differentiate and integrate, well, you can always differentiate both of them, but if you can integrate both of them, then it actually does not matter in theory which one you call your u and your dv. But if one of them's a polynomial-ish, you're probably better off calling that one your u, because then it's getting smaller. You guys okay with that? All right. Now, having just said that, let me show you something that feels like it's going to go against the grain for a moment. Well, that certainly doesn't look like anything you've ever learned. So based on what I just said a moment ago, then obviously what do I want to call u?
X to the fourth.
It seems like we would do this, and then my dv is log x dx. Actually, that's not exactly what I said before. What did I say before? If you can integrate both terms, then it never matters, in theory, which one you pick as your u. So always, in that case, always pick the polynomial as your u. Can anybody here tell me what the antiderivative of log x is?
All right.
No, because you don't know the antiderivative of log x. You only know its derivative. So I can't do that one. You only pick the polynomial to be u if you can integrate the other term. You can't integrate the other term. You with me? So you're actually kind of locked in, and it's not that. What does my u have to be?
Log.
Log, because that's the one I don't know how to integrate log. I only know how to differentiate log. So what I was saying a moment ago is if you can integrate both, then pick the polynomial thing to be the u. But you can't integrate both. So you don't have a choice really. You have to pick the u to be the log. Then your dv is x to the fourth dx. So what's your du?
1 over x.
1 over x dx. And your v? 1/5 x to the fifth. Huh. I don't think this is going to be bad. I think this is going to be kind of friendly. uv. Actually, I'm going to put the x to the fifth first. I think it reads better. Minus the integral of v du. What is that?
X to the fourth.
X to the fourth. Wait a minute, there's no more log in my answer, is there? Is that a good thing? That's a really good thing. I can integrate that one easily. What goes here?
1 over 1.
25.
1 over 25, yeah. Cool. That wasn't that bad, was it? Now, we would check it through differentiation. I'm going to leave that to you this time, but I got a product rule here. I do everything. It will work. Now, this is the answer. But just like before, I have logs, I have x to the fifth, I have fractions all over the place. This is the answer. But if I wanted to write this differently in a factored form, is there a simpler version? Again, I'm thinking calculator button pushing. Heck, if I wanted to graph this on, I want to do Desmos later, maybe graph it. We all know that the more fractions you have to work with on your calculator, the more likely you're going to enter something incorrectly. I'd rather enter as few fractions as possible. You know, I've got a TI-89 titanium. Got to throw in that because it sounds so cool and everything. But fractions just take forever to enter and stuff. Could I write this with less everythings?
Yeah.
Mm-hmm.
Multiply by 25.
Not multiply. I got to factor it. Well, do we all agree that if I factor out the x to the fifth, that'd be a good start? What fraction should I factor out?
1/5.
1/25.
That's right.
If I factor out 1/5, I still have fractions. But if I factor out 1/25, there won't be any more fractions. Isn't 1/5 the same as 5/25? So that's going to be 5 log x minus 1. Ooh. Now you don't ever have to do it, but if you were going to factor it, that would be the factorization that would be the most useful, wouldn't it? That'd be a little easier to enter into my calculator or even on computer. Yeah. How about if I got to push some buttons and do some calculating? I've got 1, 2, 3 places where I got to enter the x, and I have 2 different fractions. Here I only have 2 places to enter x, and I only have 1 fraction. I made it a little bit easier to work with. The first answer is the answer. The second one might be an improvement, though, if I've got to use it. Okay? And I'm really pointing out to your other classes that this might come up with. Do you have any classes where logarithms come up on a regular basis in answers that are not physics? Yeah, what class are they're going to come up in all the time?
Chemistry.
Chemistry, yeah.
So then, if that's the case, would you want us to always factor if we can?
No. No, I just said you never have to factor an antiderivative. I'm saying you're going to use this answer in another class, and now you got to keep going. And so in the first one we did, that's the answer. I'm in a physics class, and now I have to do that. This represents something, and I got to use this now to answer a bunch of questions. And I'm going to be doing a lot. And let's say I've got to evaluate, if this is physics, there's not one value of x. I might have to evaluate this many times. You guys ever make tables and charts all the different values, and then you're going to graph it on a log linear table, and you know, lots of work. I'm trying to minimize the amount of work if I have to use this a lot. Again, the answer is the answer, but are there versions of the answer that might be more useful to you at the time you're using it? Yeah, that's all I'm showing you. I don't need you to do this. I need you to know how to do this, because it's going to come up in another class. Okay? Everybody cool with that? Question? Yeah.
Is that x to the power of 4, or did you mean
Are you talking about the final answer?
No, above it.
Well, I'm integrating x to the fourth, so isn't the antiderivative x to the fifth?
All right. Yeah.
But it's x to the fourth because I multiplied these together. Logs actually aren't that bad. They scare us when they first come up. Okay, now I'm going to show you the worst one. And this one does come up. And a lot of people will just look this one up, but the problem with looking it up, if you don't know how it was arrived, you may not write it down correctly because it's kind of busy. And that is the situation where I have two transcendental functions in the same problem. And I'm going to do the easiest version of this, by the way. And what I mean by easiest version, in the higher level classes, it won't be e to the x, it'll be e to the 3x. And it won't be sine of x, it'll be sine of 5x. I'll put a coefficient in there, which means there's additional chain rule factors and constants that you have to work with. And that's not pleasant. And in fact, in the table of integrals, it'll actually read e to the ax and the sine of bx, and then your final answer is really complicated with a's and b's and stuff. No, I don't need you to know every version of it. I need you to know how to find this one. So then if the problem's a little more complicated, you'll automatically know how to tweak it. Because the tweakage is just algebra. The tweakage isn't really a calculus thing. So, do I know the derivative and the antiderivative of both of these terms?
Yes.
Yes. So therefore, does it matter which one I call the u and the dv in this case, do you think?
No.
No, it actually won't change anything. And it'll be the exact same amount of steps. So, I'll just write it in that order. So I'm going to let u equal e to the x, and I'll have my dv be sine x, which means my du will be e to the x dx, and my v will be what? Negative cos x? Does that look okay? Yes, no, maybe? Okay, it's too quiet. So this is uv minus the integral of v du, so that's going to be plus e to the x cos x dx. Am I going to have to do this again? Yes or no? Do I know how to do that integral? Do I know the answer to that integral? You guys know the antiderivative of e to the x cos x? I don't. No, I have to do it again because I can't integrate that one. Okay, so like we did with a moment ago when we had the x squared. So, new problem. All right, so this time, why don't we, just to make it easier on ourselves, why don't this time we say, let's let u be cos x, and let's let dv be e to the x dx. Then my du is negative sine x dx, and my v is e to the x. I had a black pen here, there it is. I should be doing all this in a different color. All right, so this is negative e to the x cos x plus, I don't really need parentheses because it's all plus. So uv, negative e to the x cos x minus the integral of v du, so that's going to be plus e to the x sine x dx. Everybody okay with that? All right, so the integral of e to the x sine x dx is, oh, these guys are going to cancel. Or did I lost something, sorry. What did I lose? Hold on. Minus, oops, hold on, I lost something somewhere. Minus v du, so plus. Oh, I'm looking at the wrong thing, sorry. That should be a point. Okay, there we go. So these guys are going to cancel, and I've got the integral of that is equal to the integral. Beautiful. Okay. What do you think?
But we're back where we started.
We're back where we started. Anybody's heads feeling like they're about to shrivel up and melt and stuff, and we did something bad. What do you think it was, CC? It wasn't step one.
Cancel.
Is it substitute in this one?
Well, no, this is still an integration by parts because I still don't know how to do that one. We did something bad, but you have to see it to know that this is why it's bad. Do you think you know what it was?
Yeah, I was wondering if it's because
we were using for use?
It's, when we started the problem, we said, let's call u the exponential function, let's call v the trig function. But in step 2, I switched that. So I'm gonna give you a money back guarantee. Whenever you switch them, everything's always gonna cancel, and you're always gonna end up back with the original problem. 100% of the time without exception. So if that doesn't happen, that means you made mistakes also. So the mistake was that I changed my choices. I flipped it over. Don't flip it over, you gotta stay the same. I'm showing you what will happen. I don't want you guys to make mistakes. Now, I'm a parent, I have a lot of kids. I've heard a lot of people say, well, you know, you let people fall out of their own tree. You gotta learn things the hard way. You do. So of course I let my children play in the freeway to teach them that that's a bad idea. No, I don't. No, and I didn't let them handle sharp objects when they were little. You know, I didn't really want them losing fingers. There's certain times you step in and say, nah, that's a bad idea. But as students, we have to struggle. We have to make mistakes, because if we don't make mistakes, we're never challenged. If you're never challenged, you're not learning anything. You gotta be challenged, you gotta make mistakes so you can fix it and then, get it right. In a 2-step integration by parts, which this will always be because I have 2 transcendental functions, you have to maintain the order all the way through to the end of the problem, or it will not work. So, let's rearrange this. So I'm gonna let my u be e to the x again, and my dv this time is gonna be cos x dx. My du is e to the x dx, and my v is sine x. So now I have negative e to the x cos x plus e to the x sine x. And then where am I? Did I lose anything? Hold on a second. And then I am plus, hold on, I lost something somewhere. Hold on. uv minus u. Did I get something back?
Minus, not plus.
Oh, here we go, thank you. Yeah, I'm looking at something, something wasn't right. I had to stare at that for a minute. So that should be, a minus, thank you. And then this should be minus, there we go, e to the x sine x. That's why I have you guys here. Okay. Does anything cancel on the right side? No, nothing's canceled, like a bunch of stuff. But there's something that's troubling you all right now. That's the original question, and it just showed up on both sides. But it doesn't cancel. It does not have the same coefficient. That has a coefficient of +1, that has a coefficient of -1. Can I add this to both sides? I'm gonna write it like that. Can I add the integral to both sides?
Mm-hmm.
In which case, what will I have on the left side then? 2 times the integral. What does 2 times the integral equal? This. You with me? The integrals did not cancel. I do not end up with everything cancel in the original question. They have different coefficients. This is the nature of this type of problem. It will always look like this. At first it feels like you did it wrong. No, you didn't do it wrong. I'm going to add this integral to both sides. Now I have 2 of them. So now I can say my original problem equals, well, I know what 2 times the integral. 2 times the integral equals this. So the integral should be half of that. Now, I'm not going to bother factoring it this time. You could. And now I'll put the plus c. This is the problem in general that gives us the most issues. Okay? This type of problem, because I have to do it twice, and it feels like something went wrong. It feels like that at first. Okay? But that's the answer. When you have 2 transcendental functions, you have no choice but to do it twice. Yes?
In that part, it's like the dv and calculated in cosine of sine, right?
Are you talking part 1 or part 2?
Part
Sorry.
2.
Okay, hold on. We're looking at this problem here. So I called u e to the x, and the dv was cos x. Oh, hold on. We've got a boo-boo there somewhere. There's a SIGN boo-boo somewhere. Hold on.
Well, it just like minus become the plus.
Hold on,
I think
no.
that's correct.
We have an SIGN error. You're right. Let's go back to the beginning. See, that's my dv, v would be the negative of the cosine, so I have negative of the rule minus the integral of v du plus that. And now that integral is uv.
The integral sign?
I have too much written too close together to. Yeah, I think we have an SIG. When I say sign there, SIG in it, sign it. Let's see if we can find it. That's my dv.
Professor Brown?
Yes.
I think it's just the integral sign is supposed to be a positive for the second part, so.
Well, no, because that would be, they shouldn't be the same sign. It should be a minus. But why, where did we lose a sign? V du, that's right. And then that integral is, if that's u, and that's my dv, and that's my v, that's my du, minus the integral of, oh, no, that's supposed to be, but it is still minus. That's still correct, but that should have been, so, does that look right? Okay, now it's correct. No, that was always a minus. That wasn't the problem. The problem was right there. Okay, so if you're checking this, something didn't cancel right. That's it. Okay. Yeah, sometimes I'm the only one that can't see it because I'm standing right at the board. Yes, this is the correct answer, and this is the correct process. We don't like this one because it's time consuming. Now, there is one. We're going to look at a whole bunch of more complicated ones tomorrow. Tomorrow. By the way, whenever I say tomorrow, you have to understand that means the next class, and yesterday, as always, the last class. That's how my brain works. So next class, we're going to look at more complicated things. Today, we're going to look at really just sort of the mainstream. But there is one that is truly evil. Now, if you look up evil in the dictionary, it won't be the first. It'll be like the 6th or 7th one, because there's so many versions. Now, this is what I refer to as the Kaiser-Soze problem. Now, does anybody know who Kaiser-Soze is? Raise your hand if you've heard that name. Okay, one of the greatest movies ever made. It's called The Usual Suspects. It was made like in the late 90s. I have seen that movie, I don't know how many times, and I'm still surprised by the ending. Because it's like got the greatest ending. It's an incredible movie. Kaiser-Soze, he's a mythical character. He's supposed to be the most evil person, literally, who ever lived, and he's alive. He is so terrible. And then you don't find out literally until the last, those who say 10 seconds of the movie or 15 seconds, who it actually is. And it's really a real person. But Kaiser-Soze, I call this the Kaiser-Soze problem. Because first of all, people don't believe he exists. And the person who actually is Kaiser-Soze is great. My favorite line of the whole movie. He says, "The greatest trick the devil ever performed." Anybody remember, what's the line?
Was convincing us that he doesn't exist.
And that's the whole point. Kaiser-Soze is supposed to be literally the devil. I call this the Kaiser-Soze problem because it looks totally innocent. It feels totally innocent, and then you'll find it's absolutely diabolical and hideous. There are different versions of the question. We're going to do this version, the secant cubed. Okay? And you will understand why I call it the Kaiser-Soze problem, because it looks absolutely innocent, piece of cake, nothing tricky. Now, I don't know the antiderivative of a trig function raised to a power, but we do know the antiderivative of secant squared, don't we? We also know the antiderivative of secant to the first power. So you got any suggestions here? Let's make it an integration by parts problem.
Split in secant squared times secant.
Okay, first step, let's make it, how about secant x, secant squared x. Is that legal? Well, yeah, but it also, I can use integration by parts now. I can either integrate the secant or I can differentiate the secant. I can integrate the secant squared or I can differentiate the secant squared. Do you all agree? Which route feels less painful? Which one do I want to integrate properly?
Secant squared.
Probably secant squared. Yeah, I think that would make it a little cleaner. But this doesn't feel bad at all. This feels like it's going to be a one-step and out kind of thing. All right, so we're going to say, let's let u equal secant x, and dv is secant squared x dx. So then du is, what's the derivative of the secant? This is why you have the formulas right next to you in case you can't remember.
Tangent squared.
No.
No.
Tangent.
Tangent, secant.
Secant tangent, yeah. Again, I'm serious when I said this is why you want the formulas right next to you, in case you just can't remember stuff like that. And the antiderivative of secant squared, what function has a derivative of secant squared? Tangent, yeah. Yes? We're good with that? Okay, so uv minus the integral of v du. And that'll be secant x tan squared x. Okay? Any suggestions? Well, I could say let u be secant x like I did before and let dv be tan squared, but that doesn't look like one that I know. I could mess around and manipulate it.
Secant tangent, and then
Secant tangent is something I know, agreed? So I could make one of them be secant tangent. I could make the dv be secant tangent. And then the u would just be tangent. But if I make the, will I be undoing my work if I do that? So maybe that's not the way. Is that what you're going to say? If I make one of them be secant tangent, does everyone see that? I might be undoing it again. So maybe that one won't work. This doesn't look like it should be terrible. Are there any Pythagorean identities here? What do you think?
Isn't that?
We seem to have hit a roadblock. It is absolutely correct to call one of them tangent and the other one secant tangent. But if I call the dv secant tangent, then the v will be back to secant, and it does feel like we might be undoing that because it feels like I might have switched order. So I'm going to avoid that one. Is there a Pythagorean identity involving tan squared?
Yes, tan squared plus 1 is equal to secant
Okay, so this is secant squared
minus 1.
minus 1? Yes? Is that a good idea, maybe to throw that in there?
Yeah.
Okay, so now we've got,
Secant.
how about if I rewrite this as,
Minus secant x.
so I'll put this, it's this answer. So what does that give me now? That's secant x tan x minus the integral of secant cubed x dx. I'll break it into two integrals. Plus the integral of secant x dx. Are you with me?
Yeah.
Will that work?
Yeah.
It's getting more complicated, isn't it?
About to say, how do we have a secant cubed back? We just got rid of the secant.
No, it does work.
we just got rid of
But we're, but is it the same sign? Is it the same SIGN? Remember when we did, well, we did that one over there. We ran into the same thing. Original problem, same thing, but opposite sign on this side, and we were able to add it over. What do you notice?
Secant
It does have the opposite sign, so is that okay, at least?
Okay.
That at least we're alive. We're not gonna drown here. Okay? Can I throw that to the other side?
Yeah.
So then what would I have? I'd have two secant cubed x's. And what do I have on the right side? I have secant x tan x. What's the antiderivative of the secant function?
Secant.
That's a little more obscure.
Secant x. Oh, no, log.
Do we have enough to finish now? So what does the secant cubed look like? Half of that. I'm inclined to put half as a coefficient rather than half of a quantity. I think half of a quantity doesn't make my life easier. I think just putting the halves in. Now I'll put the plus c. The only check is to differentiate. I don't really want to do that one. I can, you know, icky product rule and way worse chain rule, but we would all eventually get a right answer, I would hope. Eventually. Wow. This seems so easy after the first step, didn't it? We did more work on this one than we did on that one. It is often the case that if you look at something that doesn't look like you can do it, but we broke it apart, we were clever with it. Next day we're going to do a lot of the clever ones. That's what I'll call them. We'll do things that you're looking at the problem, you're going, this can't actually be answered. It cannot be answered directly, but if I think of it as an integration by parts, I'm going to give you a hint. We're going to integrate next day things like, I want to integrate the inverse tangent. Not times anything, just by itself. I want to integrate the natural log. I want to integrate inverse trigs in general. I want to integrate things that don't have antiderivatives in general by making them integration by parts problems. And then by doing that, we'll find there's a lot of problems we actually can get the answer. What we're conditioned to is, here's the integral, here's the answer, there's no work in between, it's a straight antiderivative formula that involves exactly one term. That's what you did in Calc 1. I differentiate one term, I get one term, I integrate one term, I get back. What are you noticing now though? We're integrating one term and we're getting multiple terms back. Because it's not a simple antiderivative formula. The technique is making it so that automatically I'm getting multiple terms. So if I said in Calc 1, by the way, this is a fair Calc 1 question. I want you to differentiate this because you know how. You would differentiate, you'd manipulate it, you'd simplify it, and eventually, hopefully you'd get secant cubed at the end. And you go, wow, my derivative really got clean after all this mess. That's kind of the nature of things. So if the integration cannot be done in one step because it's not a simple antiderivative, then you must apply technique. And we're going to learn several. There are 3 main techniques, and then there's some minor techniques. I don't know what day. Hold on, I'll tell you exactly. Pull out my schedule here for a second. If I can find it. I have it in here. Ah, here it is. All right. On the 21st, which is 2 weeks from Wednesday, the last integration technique you're going to learn is the last integration technique you will ever learn the rest of your life. If you study math forevermore and into the next century and beyond, that's it. Every technique that exists in the history of the world you will know in another 2 weeks. Wait a minute. We're not even a third of the way through Calc 2. How's that possible? No, you'll have learned every technique that currently exists. Then you're going to learn how to use them to answer questions and all the variations. But in terms of just straight up integrating, you're going to have everything there is. Last semester you learned all the things that have one step. If the derivative gave me this, the antiderivative gave me this because there was no product rule, no quotient rules, nothing complicated. This semester, I now am applying techniques to more complicated things, so my answers are a bit more complicated. But in a short amount of time, everything that could be integrated. Does that mean that everything can be integrated then? This is a tricky question. Can everything be integrated? I'll give you a simple example. We can all integrate this. What about this? Make anything you want for f of x. Make any function other than just x. Well, with very few exceptions, dead end. Can't do anything with it. Easy. Most of the time, impossible. So what do we spend a significant amount of this course on? These ones. My favorite problems will be the ones that cannot be answered. There is no antiderivative, but we're going to answer it anyway, because we're going to learn other techniques, backdoor techniques, that'll get us there. And it's when we get there, it's very, very cool mathematics. But for every integral you can do, there are an infinite number of variations. Look at the right side. An infinite number of variations that can't be done. Yikes. So we'll learn every way of manipulating things, because a lot of times in real life, the question is posed and I need to answer it in order to finish the problem, but I might not be able to give you a simple antiderivative. So we will learn other ways to get around the problem. It's powerful stuff. But that's kind of where things will be headed. All right, we do the roll thing, and then I'm going to kick you guys out of here. I'll be in my office shortly. Chase, can you go ahead and stop it? Yeah, I really don't like